Hi, I'm Orion, and this is our presentation of Defending Against Disinformation Attacks in Open Domain Question Answering. This is a work done at Johns Hopkins University and is joint with Aleem, Nathaniel, Don, and Benjamin. So what are modern open domain question answering systems? One that I think we're all familiar with is Google. So for example, if you type in who invented the toaster into Google, you're going to get some results with a varying amount of text, and then some links where you can click on in order to see more results. However, perhaps a more cutting edge system could be something like Perplexity AI, where when you type in who invented the toaster, you're going to get an answer, also a list of sources with citations to those sources. And note that these sources are usually from open web websites or places with trusted information like Wikipedia. However, what if you have fake information? So on the right here, we have a person named Alan McMasters, and this is from their Wikipedia page, where it talks about how they're the inventor of the toaster. In fact, this person was, mildly famous. They were even nominated by the British public to appear on the next £50 note by the Bank of England in 2018. However, in 2022, it was noticed that a student had created this Wikipedia page 10 years prior-ish, and it turns out that this was all completely fake information. And yet this fake information on Wikipedia had been propagated and retold by museums, news outlets, etc., and became this self-fulfilling cycle of information. So if this is happening on Wikipedia, are there more malicious attacks that are happening out on the open internet that we just can't see because they don't all have the oversight that Wikipedia has, where we can track down these edits and see these sorts of details? So what happens to ODQA systems when there is disinformation? So we start with a question, like where was Barack Obama born, and a knowledge base, or a collection of documents. It can be the open web, Wikipedia, whatever you choose. You then search over that corpus. You find a collection of documents. Let's say here in red are the documents that are poisoned, they're disinformation. And the documents in blue are those that are correct documents and they don't have the disinformation. So for example, the ones that have been poisoned say that Obama was born in Kenya, which is incorrect. So here we have this group of retrieved documents, and typically what happens with an open domain question answering system is you just feed all these documents into some question answering model and it generates one answer. So here the model would probably predict something like Kenya, given that the top documents and a majority of them have that incorrect information. So can we defend against this? Our intuition is that the internet is diverse. So can we use this diverse and redundant information to fact check itself? For example, we have Barack Obama's Wikipedia page that talks about how he was born in Hawaii. But say that information was then poisoned, and now we have this disinformation that Obama was born in Kenya and is incorrect. However, on Wikipedia, there also exists other redundant information. For example, maybe his mother's page, Anne's page, which talks about how he was born in Honolulu. So using this motivation, we come up with the following method. We first, like the other one, take in a question, look through some corpus, and predict an answer, just like the original system. We then add a few more steps. We take the query and do query augmentation, where we ask a large language model to generate new diverse questions that would still answer the original. These questions might look like, what is Barack Obama's city of birth? Or what hospital was Barack Obama born in? Note that these aren't exact paraphrases, but they are very close and will provide similar information as the original. We then take these augmented questions and do search with them, just like we would if they were the original question. These both return a new set of documents. You can see here documents 4 and 5 were not found in the original query. And then finally, we perform regular question answering on each of these subsets, which return the answers Hawaii. The step is to combine these answers into one final aggregated answer. We aggregate them using our new calibration method, confidence from answer redundancy, or CAR, which takes them in and their retrieved passages and generates one final answer, Hawaii. We note that although this diagram looks like a majority vote, we note that our method actually outperforms majority votes by a significant margin, as we'll show later. So let's talk about what two things our method needs to work. First, we need query augmentations to find and retrieve new documents so that we can take advantage of this redundancy. We also need to aggregate this information in combination with the original. So let's dive into each of these topics in detail. What experimental settings do we use? We use Wikipedia as our example corpus and Trivia QA and natural questions as our queries. We simulate attacks by poisoning articles using existing methods in the literature from Longpree et al. 2022. We poison the top N articles retrieved by the original ODQA system to simulate an attack, and we vary N, as you'll see in the results. And the poisoning is done per query, so poisoning from one query doesn't impact any other queries. So we want to gather diverse new passages by asking an LLM to generate similar but diverse questions, with the goal of finding new passages from novel Wikipedia articles. So as another example of query augmentation, we have the original query, in which year did Picasso die? With the augmented questions, when did Picasso die? How old was Picasso when he died? And what was Picasso's cause of death? Augmented questions ask for new details that retrieval models will search for and hopefully find new and diverse passages. But how well do they work in retrieving new passages? Here we see a plot of Trivia QA searching over Wikipedia for each of these augmented questions, where the x-axis shows the number of new passages that augmented question retrieved compared to the original. We consistently find a new set of passages, pretty evenly distributed between 0 and 100. This is because the corpora contains redundant information. So how can we use this additional redundant information? As a reminder, we have information such as Barack Obama was born in Kenya. This is the disinformation. We have other redundant information such as his mother's page or his father's page and so on. And so when we have predictions from all of these different systems, how do we combine them? We do this from what we call confidence from answer redundancy, or CAR. And this works in a very simple manner. Is the original predicted answer present in K of the documents retrieved? And if that is true, we're going to use the original prediction because we're confident given the answer redundancy. If that's not, we are going to use a majority vote over the new predictions, excluding the original. So how well does this method perform compared to the baselines? Let's start by looking at the original ODQA model. We used a variety of models in the paper as well as 2 datasets, but for the sake of this video, I'm only going to show the Atlas model on the Trivia QA dataset. The green line here is the original ODQA system. Note that we use only questions that the original ODQA model answered correctly on, so that way we can show the effect of the misinformation. So by definition, at 0 poisoned articles, it's at 100% exact match, 1.0. We vary the number of articles that are poisoned from 0 to 100, as there are only 100 passages that Atlas and the other models we use take as input. So at 100 poisoned articles, all of them have been poisoned. We can see that this significantly decreases the exact match as it goes from 0 to 100, which makes sense since all the passages will have been poisoned. Let's look at the other baselines. If we take the augmented queries and pick one at random and use the answer that it predicted, we get this orange plot, the random line, that significantly underperforms the original method. We can also take a majority vote over all augmented questions and the original question. This is in blue. We note that this still underperforms the original method. However, if we look at our new proposed method, confidence from answer redundancy, which we call redundancy in pink, we see that it significantly outperforms the original method by about 20 exact match points at several points. Overall, we can see that redundancy provides an effective way to defend against disinformation attacks. So how many query augmentations do you need for our method to be successful? We show here just one setting, the one article poison setting, where the original baseline method has an exact match score of 50.1%. We can show that even just using one augmented query with our redundancy method provides more than a 10-point exact match gain, and that increasing the number of augmented queries only increases the score. We also have a lot of other fun ablations that I don't have time to talk about here. This includes using Vicuna and Llama instead of GPT-3 as our large language model. It includes results on more poisoning strategies, as well as more QA data and more models, such as natural questions and fusion and decoder. So in summary, we show that we can use large language models to augment queries in order to find redundant information, and that redundant information provides useful calibration information for QA systems and can improve disinformation defense by over 20 plus points. And even just using one of those additional queries can recover 10 plus exact match points. Thanks so much for listening to this presentation. If you have any questions, feel free to check out the paper. Please shoot me an email. Thanks.